everyone, welcome to this exciting journey into the world of statistics for data science. Have you ever wondered how data transforms from raw numbers into powerful insights that drive decisions? Well, statistics is the magic behind it all. Today, we will uncover how statistical methods help us summarize data, model uncertainty, test hypotheses, and find relationships that can predict the future. So, buckle up. We are about to turn numbers into knowledge. But before we move on, imagine transforming your career with one of the hottest skills today, data science and generative AI. Ranked as the #1 data science program by Economic Times, the professional certificate in data science and generative AI from Purdue University and Simplilearn equips you with hands-on learning in Python, machine learning, deep learning, generative AI tools like ChatGPT, and with masterclasses from Purdue faculty and IBM experts. Plus, real-world projects. This 6-month program opened doors to high-demand roles across the industries. Boost your career with Purdue's world-class training. So hurry up and enroll now and can find the course link below. Now, before we get started, here's a quick quiz question for you. Let me know what is the main purpose of statistics in data science. Your options are memorize numbers, make sense of data, or just create charts. Let me know your answers in the comment section below. So guys, without any further ado, let's get started. Now to start off, here's a key question. What are statistics in data science? Now statistics is the science of collecting, analyzing, and interpreting data. By applying statistical methods, we can uncover patterns in the data and make informed decisions. Now as we continue, you notice how these essential concepts will form the backbone of many data science practices. Let's explore the key functions of statistics in data science. First, statistics help summarize data using measures like mean, median, and variance. Next, it models uncertainty with probability and distributions, so we can better understand risk and variability in our data. It also tests hypotheses, such as when we use A/B testing to compare different outcomes. Statistics finds relationship through methods like regression and correlation, revealing how variables impact each other. And finally, all these tools enable data-driven decision-making, turning raw numbers into actionable insights. Now let's talk about why does statistics matter in data science. Statistics form the backbone of data science, providing the mathematical framework needed to make sense of data and draw reliable conclusions. Without statistics, it would be impossible to turn raw data into meaningful insights or make confident, evidence-based decisions. Now, let's have a look at the main branches of statistics: descriptive statistics and inferential statistics. So first, let's talk about the definition. Then we have got methods and measures. Now in the case of descriptive statistics, now let's have a look at the main branches of statistics. So basically there are two core branches: descriptive statistics and inferential statistics. Descriptive statistics summarizes and describes data using measures like mean, median, mode, range, and standard deviation. Its purpose is to organize and present data, typically with charts, graph, or summary tables. The scope of descriptive statistics is limited to the sample data itself. Now, on the other hand, inferential statistics makes inferences about populations based on samples. It uses methods like hypothesis testing, confidence intervals, and regression. The purpose here is to draw conclusions and make predictions with common examples including A/B testing and survey analysis. The scope of inferential statistics extends beyond the sample to the larger population. Understanding both these branches is essential for analyzing and interpreting data in any data science project. Now, let's take a closer look at the descriptive statistics, starting with measures of central tendency. The first measure here is mean, which is the average of all the values, simply calculated as the sum of all the data points divided by the total count. Next is the median, which represents the middle value when the data is sorted from lowest to highest. This is especially useful when dealing with skewed distributions. And finally, the mode is the most frequently occurring value in the data set, helping us identify common patterns or repeated outcomes. Let's continue our deep dive into descriptive statistics by looking at the measures of variability. First, we've got the range. This is simply the difference between the maximum and minimum value in a data set, showing us the spread of our data, which measures the average of the square differences from the mean. This tells us how much the values in our data set differ from the average. Closely related is the standard deviation, which is the square root of the variance. It gives us a more intuitive sense of how much the values typically deviate from the mean. And finally, we've got the interquartile range, or we say IQR. This shows us the range of the middle 50% of our data, helping us understand how data is distributed across the center and avoid the effect of outliers. Understanding these 4 measures allows us to summarize not just the center of our data, but how spread out and varied our data set is. Now, let's look at some practical applications of descriptive statistics. One major use is the data exploration and summarization, where we quickly get an overview and basic understanding of complex data sets, helping track performance and detect problems early in fields like manufacturing or operations. And finally, they are central to business reporting and dashboards, where concise summaries are essential for managers to review trends and make data-driven decisions. So in short, descriptive statistics help transform raw data into clear, actionable information across many business, scientific, and operational contexts. Let's explore the first type of data in statistics, qualitative or categorical data. This type of data includes descriptive information that cannot be measured numerically, such as categories or labels, and yes or no responses. These are all about qualities or characteristics rather than quantities. Qualitative data can be further divided into 2 types: nominal, where the categories have no specific order, and ordinal, where the categories do have an order or ranking. Recognizing and classifying qualitative data is very important, as it affects how information is analyzed and interpreted in statistics. Now let's discuss the second main type of data in statistics, which is quantitative or numerical data. This type of data includes information that can be measured and expressed with numbers, making it ideal for mathematical analysis. Quantitative data is further divided into 2 main categories. First, there is discrete data. These are countable values with specific fixed points, such as the number of students, cars sold, or website clicks. Second, there is continuous data, which includes infinite possible values within a given range. Examples of continuous data include height, weight, temperature, or time. Understanding the distinction between discrete and continuous data is very important, as it determines which statistical methods and visualizations will be most appropriate. Now let's dive into the fundamentals of probability. Probability measures the likelihood of an event occurring, and it's always expressed as a value between 0 and 1. Here are some key concepts. If the probability or P equals to 0, that means the event will never occur. If P is equals to 1, the event will always occur. And if P is equals to 0.5, the event has an equal chance of occurring or not occurring. It's truly a 50-50% scenario. Now, understanding these basic principles help us quantify uncertainty and make informed predictions about future outcomes. Now, let's look at the different types of probability. First, there's classical probability. This is based on equally likely outcomes, such as flipping a fair coin or rolling a balanced die. Next, empirical probability, which relies on observed frequency. It's calculated from actual data, such as the proportion of rainy days over the past month. Let's say, for example, the probability of it's raining today given that it's cloudy. Understanding these 3 types help us choose the right approach for different situations, whether we are predicting outcomes, analyzing data, or making decisions under uncertainty. Now, probability has a wide range of powerful applications in data science. First of all, it is used in predictive modeling and machine learning, where algorithms estimate future outcomes based on existing data. Probability also plays a key role in risk management and decision making, helping businesses and researchers evaluate the likelihood of different scenarios and plan accordingly. Conditional probability, calculating the chance of one event given that the another has occurred. This is crucial in fields like healthcare, fraud detection, and marketing analytics. And finally, probability is foundational in A/B testing and experimental design, allowing us to measure the effectiveness of new strategies or products. These applications show how probability enables smarter, evidence-driven progress in modern data science. Let's look at one of the most common probability distributions, the normal distribution. This distribution is famous for its bell-shaped symmetric curve, which shows that most values cluster around the mean, with fewer and fewer values appearing as you move away from the center. Now, many natural phenomena like heights, test scores, and measurement errors tend to follow this pattern, making the normal distribution a key concept in statistics. It's characterized by two main parameters, the mean, which determines the center of the curve, and the standard deviation, which controls its spread. Recognizing the distribution helps analysts make predictions, calculate probabilities, and apply statistical techniques to real-world data. Next, let's explore the binomial distribution, which is another common probability distribution. The binomial distribution is discrete and is used for situations with binary outcomes like success or failure. It is based on a fixed number of trials where each trial has a constant probability of success, such as flipping a coin a certain number of times or tracking pass-fail rates. Examples of binomial experiment includes coin flips and measuring how many students pass or fail a test. This distribution helps us model and analyze outcomes when only two possibilities exist in each trial. Now, let's focus on the Poisson distribution, another key type of probability distribution. The Poisson distribution is a discrete distribution specifically used to model rare events. It's particularly helpful for modeling events that occur independently over a fixed interval of time or space. For example, it predicts how many times an event, like a customer arriving on a website receiving a visit, might happen in a certain period. Typical examples include customer arrivals at a store, defect rates in manufacturing, or counts of website visits over a set period. This distribution is a great tool for understanding and predicting random independent events that don't happen very often but are important to track. It's a branch that allows us to make inferences, predictions, or generalizations about a larger population using sample data. Here are some key concepts. First is the population versus sample. The population represents the entire group we want to know about, while the sample is the subset we actually collect data from. Next concept is sampling distribution, which refers to the distribution of a statistic across multiple samples from the same population. Standard error measures how much the sample statistic is expected to vary due to random sampling. And finally, margin of error tells us how much we can expect our estimates to differ from the true population value. Together, these concepts form the foundation for drawing reliable insights from sample data in inferential statistics. Let's review some of the main techniques used in inferential statistics. First, we've got hypothesis testing. This method allows us to test claims or ideas about population parameters based on sample data, helping us determine if observed results are statistically significant and reliability of our estimate. Next are confidence intervals. These provide a range of likely values for a population parameter, giving us a sense of possible variation, reliability of our estimate. And lastly, regression analysis is used to model and analyze the relationships between variables, allowing us to make predictions, uncover trends, and understand how changes in one factor might affect another. Now, let's walk through the hypothesis testing process. The first step is to formulate hypothesis. Start with null hypothesis, represented as H0, which states that there is no effect or difference. Then there's the alternative hypothesis, represented as H1, which suggests that an effect or difference does exist. Now, after setting up the hypothesis, the next step is to choose a significance level noted by alpha. Common choices for significance levels include 0.05, 5%, 0.01, 1%, 0.010, which is 10%. The significance level is important because it controls the likelihood of making a type 1 error, also known as false positive, and now, each step in the process is critical for ensuring that statistical results are both meaningful and reliable. The next step is to collect and analyze sample data. Ensure the data is represented by choosing a good sample. Then calculate the appropriate and test statistic for your hypothesis test. Once that's done, it's time to make a decision. Compare the p-value to the chosen significance level alpha. Now, if the p-value is less than or equals to alpha, you reject the null hypothesis. If the p-value is greater than alpha, you fail to reject the null hypothesis. And finally, interpret your results. Draw your conclusions with respect to the context and problem at hand, always keeping the bigger picture in mind. Following these steps helps ensure your hypothesis test is robust, clear, and meaningful. Let's review the common types of hypothesis test used in statistics. The one sample test compares the mean of a sample to a known value, and the one sample Z test is used when the population standard deviation is known. Next, we have two sample tests. The independent samples t-test compares to the means of two different groups, while paired samples t-test compares before and after measurements for the same subject. For categorical data test, the chi-square test checks for the independence or goodness of fit. And Fisher's exact test is useful for small sample sizes. And lastly, non-parametric tests such as the Mann-Whitney U-test and Wilcoxon-signed rank test serve as alternatives to the t-test when data doesn't meet certain parametric assumptions. Choosing the right hypothesis test depends on your data type and the specific question you want to answer. Let's explore the central limit theorem, or CLT, a foundation for inferential statistics. The central limit theorem states that as the sample size increases, the distribution of sample means approaches a normal distribution, even if the original data isn't normally distributed. This sample works for any population distribution, making it incredibly powerful. Now, for good results, the sample size should typically be 30 or more. What's interesting is the sample mean distribution, which will have the same mean as the population. The standard error, which measures variability by the sample mean, equals sigma divided by the square root of n, and this gets smaller as the sample size grows. And finally, the formula shown here, which is z is equals to x minus nu divided by sigma over the square root of n. Let's standardize and compare sample means. The CLT makes most parametric statistics possible and is the backbone for many statistical tests. Let's review the main types of regression analysis which are used to model and understand relationships between variables. First up is linear regression. This technique analyzes the relationship between a continuous variable and another variable, resulting in a straight line. It's commonly used in predicting sales or prices. Next is logistic regression. Unlike linear regression, this method is used for binary outcomes, helping estimate probabilities such as whether an email is spam or a patient has a disease. Moving to multiple regression, this allows us to account for the effect of several variables at once, modeling more complex relationships like determining house prices. Lastly, polynomial regression, which is used for non-linear relationships. The resulting curve, rather than a straight line, lets us capture growth trends and other patterns that aren't linear. Understanding these types of regression help analysts choose the right model for the data and business's problem at hand. Let's clarify the important differences between correlation and causation. Correlation is statistical measure of how two variables move together. Correlation values range from -10 to +1. But remember, correlation does not imply causation. On the other hand, causation means that one variable actually causes changes in another. Establishing causation requires controlled experimentation and is much stronger relationship than simple correlation. Always be careful when interpreting results. Just because two variables move together doesn't mean one caused the other. Let's look at some common problems with interpreting correlation and causation. First is the third variable problem, which happens when a hidden variable affects both variables in a question, leading to a misleading connection. There's also this directionality problem where it's unclear which variable is causing others to change. But both are actually caused by a third variable, which is the hot weather. This demonstrates that correlation does not mean one variable causes the other, so always look for hidden factors before assuming causation. Let's talk about statistical errors, specifically type 1 and type 2 errors. Type 1 error, also called as false positive, occurs when we reject the true null hypothesis. In other words, we wrongly conclude there's an effect when there actually isn't. The probability of making this error is equal to the significance level alpha. For example, concluding a drug works when it actually doesn't. On the other hand, type 2 error is false negative, means failing to reject a false null hypothesis. That's when we miss a real effect or difference. The probability of type 2 error is beta. For example, missing the real effect of a drug and saying it doesn't work when it actually does. Understanding these errors is key for designing good experiments and interpreting statistical results properly. Let's look at 3 common sampling methods used in statistics. The first one is random sampling. Here, every individual in the population has an equal chance of being selected. Where every nth individual is chosen, random sampling is crucial for ensuring representative sample. Next is stratified sampling. The population is divided onto homogeneous subgroups or strata, and then a random sample is drawn from each group. This approach makes sure all the groups are represented in the sample. And finally, cluster sampling divides the population into clusters, often based on geography. Entire clusters are then randomly selected. It's cost effective and useful for large, spread out populations. Choosing the right method ensures the data truly represents the whole population and strengthens the study's conclusions. So guys, let's wrap up with some real-world applications of statistics. In business analytics, statistics are used for A/B testing to optimize websites, customer segmentation, and targeting, sales forecasting and demand planning, and quality control, and also process improvement. These techniques help businesses make smarter, data-driven decisions every day. Statistics play a vital role in healthcare and medicine as well. They are key for analyzing clinical trial results, conducting epidemiological studies, evaluating treatment, effectiveness, and identifying risk factors. By using these approaches, healthcare researchers and practitioners can improve patient outcomes in public health. From businesses to medicine, statistics transform raw information into actionable insights that create real impact. Statistics has a huge impact in technology, data science, and finance, and power recommender systems that personalize what users see. In finance, statistics help with risk assessment and management, optimizing investment portfolios, determining credit scores, and supporting market research and analysis. Now, these applications show how statistical techniques help make smarter decisions and solve complex challenges across high-impact industries. And that's a wrap-up on our journey into the world of statistics for data science. We have explored how statistics help us summarize data, understand uncertainty, test hypotheses, find relationships, and make informed decisions. From descriptive statistics to probability, distributions, regression, and real-world applications, you now have the foundation to start analyzing data like a pro. Remember, every data set tells a story, and with statistics, you have the tools to uncover it. Now, if you enjoyed this session, don't forget to like, share, and subscribe for more such data science insights. Until then, thank you and keep learning with Simplilearn.